The point here is this, that if you know calculus, you can actually find the vertex without getting to the vertex form. One way is just creating the vertex form. Another way is to doing calculus. Okay, let's say our function, we don't know what it describes. It potentially might be a utility function. So that's my motivation. I'm trying not to talk about it, but I'm kind of talking about it. So let's say it's a is negative, by the way, minus 2x squared plus 400x, let's say, plus 0, right? We got a, b, c, whatever, right? So no need to see. Let's say we don't want to see. Okay, now, what's the difference between the a value being positive and a value being negative? You remember what it defines? It defines a positive means you're going up eventually, a negative means you're going down eventually. Now, in terms of calculus, the situation of going up eventually means that you were always trying to go up anyway. Even when you were going down, you were still trying to go up. So starting very negatively sloped down, you were always trying to become less negatively sloped down. And there was a moment in that process when you became fully horizontal, when you kind of completely negated your vertical, yes. And then, because you continued that motion, because there was something behind you pushing you, some force, some mental state, whatever, demand, whatever, right? Demand, utility, need, acceleration if it's physics, you continued in that same manner, and you basically became going up, as you intended, right? But if you think in terms of your slope, it's not like you were always going up, right? In terms of your slope, you were going down up until the vertex. That's why vertex is important, because it's a transition. Every vertex is a transition. It is either one or the other. Well, in this case, it will be the maximum. In this case, it was the minimum. If the direction of the slope before was down and after up, it means you just reached the bottom. You can't reach the top doing that, right? That's like seeing the picture and making that statement. But I want you to also be able to create the picture in your mind, seeing the statement. Other way around. From the words, from the formal to the visual, right? From the visual to the words, that's good. But from the words, let's say, I tell you that the slope was positive, up until some point, and then the slope became negative. So what can you deduce from that? You can deduce for sure that you must have reached at least the local, but maximum. It must have been the peak along the way, right? Because otherwise, your slope could have never become negative after being positive. Positive means going up. Alright, so in terms of the slope, there is definitely some differentiation, some change. It's not the same. It was positive, then it was negative. It was negative, then it was positive. But what was it that was always same? Something must have been exactly same all the time in order for this motion to take place, right? This intent, the drive. What was the drive? It would be the drive to go up here and the drive to go down here, right? He had the drive to go down. His stance was very positive, but he continued to go less and less and less and less and less. He was always losing his positivity. This guy was always losing his negativity. This is the second derivative. The slope is the first derivative. The graph itself is the original function. So the original function is the beginning. You can think about it as zero derivative, no derivative. It's the original, right? You haven't done anything, you just took it as for granted. It's the beginning, it's the starting, the original. In your cases here, it's the utility function. Utility function is a quadratic function, and it does have a negative a value, because it must be representing something that goes up and then down. Right? Utility. If you want something and you don't have it, you kind of need it, let's say, right? In a perfect world. So you have utility, you have value for it, you have some demand for it, right? It provides some consumer surplus to you potentially. You want it, you know you'll have to pay for it, you know there will be cost. But there is some amount that you want. And then there's a point where you reach that amount which maximizes everything. Maximizes utility for you, granted experience, whatever. Maximizes the consumer surplus, right? Gives you complete total marginal utility. And then after that point, it starts to diminish, right? Yes, so to find the perfect situation is basically to find the vertex of the utility function. And it is a parabola, which means it's to find the place where the derivative is zero. Because derivative, so now let's do calculus. Calculus allows you to find those positions. Calculus allows you to figure out all slopes at any point, at any moment of any function whatsoever. And not approximating, exactly knowing, pinpointing it. Happened here, right? So now, in this case, actually, because it's a simple case, you can actually figure out where that happened even without doing calculus. Because you can probably figure out what are the two roots for this parabola, or whatever, this guy's parabola, what are the two x-intercepts, and you can find the place right in the middle and say, well, that must be the vertex, right? That must be the middle, right? It's a symmetric shape, must be right in the middle. So, but, if you do calculus, you would say, for me, the slope, the idea of the slope, which is defined pre-calculus as change in answers divided by change in inputs, delta y over delta x, which has another name, rise over run. The slope is a more technical name. The slant It used to be called the slant, but I don't think we've been using that word too much in the last couple of decades. The slant, the slope, delta y, delta x, rise or run, and there is another name, the first derivative. Of the original function. What is derivative? What are you trying to derive? You're trying to derive some extra knowledge about the original thing. What are you trying to derive? You're trying to derive some extra knowledge about the original thing. What kind of knowledge are you interested in? When you do differentiation, when you do calculus, and you have your expression of original function, and you have a graph of it, maybe, maybe not, what you're deriving is the information about the slope of that function's graph. Rate of change. The way how it moves. Its direction. Its directionality, right? So I guess there's another even name here. The slope, the first derivative, the rate of change. The most famous name. The rate of change. Change. If you know how things change, you know how they move in time and space, right? Same, it doesn't matter whatever it is, right? Okay, so these are all the same synonyms of the same idea. And the first derivative of any function, if you start with wherever you start, if you take the derivative of that thing, you are talking about the slope of the graph of that thing, or the rate of change of that thing, right? Or the rise of a run of that thing, or whatever, the slope. So now, let's try to do it. So we already have our original function, right? So let us, for a second, forget about the pictures and go full-fledged calculus. I'm going to write down now here the label that we usually use instead of writing delta y over delta x. Now, Gottfried Leibniz was one of the contemporaries of Isaac Newton 350 years ago, almost 400 years ago. He also was one of the guys who figured out the differentiation, defining rise over run, to understood that the slope is this. He instead of writing delta, he just wrote d. So we still use that. D something over d something, right? And you see it a lot in your text. Right, it's actually not derivative, it just means delta. Change. Change in answers over change in inputs. D is delta, it's the Greek delta. So just instead of writing a triangle, writing like English, like Latin D. It was German, same thing, D. Okay, so that's this. And if it's first, it's first. So usually we don't write it, right? But there's a way of actually writing 2 here, and then you'll have to write 2 there at the whole thing. It's just a little bit weird, like we write 2 here, but if it's 2, it's a second derivative. It's like you're doing the same thing again. But now you're applying it onto the first derivative. You kind of continue doing the same thing. Now we have to figure out what is that thing. How do we do that, right? How do we get the differentiation? We use the rules that were invented by him and by Isaac Newton. Therefore, I'm going to write down another style that I prefer more. This is more scientific. Another label. That's one, but there's another label that we use, which is simpler. That's this. Just prime. So instead of saying dy dx, you can just say f prime x. When you see prime, 1 prime, first derivative. 2 primes, 2 derivatives, whatever. 25 primes, right? But in the meaningful things, we usually go only to the second derivative. Because second derivative already talks about the drive, the intention behind the whole thing, the acceleration, right? Like going beyond that is a little bit too much most of the time. Oh, I forgot. Of course, prime. Yeah, first derivative is not just f, right? You see, it's like when you see 0 here, technically you can write 0 there. That means original function. That means no differentiation, right? If you put there 1, that's another style, by the way. Little tiny brackets, and then put numbers there. Now, how do you differentiate an original function? How do you differentiate any function, right? Obviously, when you differentiate something, that something plays the role of the original function. How do you differentiate? You use the rules. What are the rules? The whole conversation is about the slope, right? Derivative is a slope. And the slope is conditioned to exist. It's a consequence of what? Mostly, it's a consequence of the number in front of the variable. Remember, right? With the lines, if you have number, it's the slope, right? It's the slope, right? It's the k value, whatever. So those numbers, which we call scalar multiples, those scalar multiples will always survive the act of differentiation. They will never disappear. Anytime you have a number that is multiplied to some variable, that number will always be part of the answer, of the differentiation, of the derivative, okay? So minus 2 here will stay. But then, there is something you have to do with the term that is a variable, but has power. What do you do with the power of the variable? You bring it down. That's called a power rule. You bring it down, so this 2 comes down. Yeah. Yes, exactly. Okay, yeah, 2 minus 1, right? And then, you do the same thing here, right? 400 times 1, but it becomes x0, which is anything to 0 is 1. Yes, exactly. You see? Same rule, right? So, and here we actually also used the rule that tells you that when you add or subtract 2 statements, you can just go on. It's linearly translatable, right? Don't worry about plus minus. The differentiation just flows through it. But it doesn't flow through multiplication division. Multiplication division, remember, right? There's a product rule, there's a quotient rule, right? And there's a chain rule, which means that when you multiply 2 statements, you can't just multiply. You have to do something crazier than that. It's not that easy. But when you add subtract, you can just go on like step by step. Also, when you have 2 functions inside of each other, when you have composite statements, you also cannot just do one by one. You have to use a chain rule. What we have to do right now is understand that when you take the first derivative, you actually find the slope. You find the description of the slope, how slope behaves. So you basically get the description of the rate of change. or rise over run. Same thing, same idea. So the rise over run description of the rise over run of this function is minus 4 times x plus 400. That is the first derivative of the original function, f prime x. Now, if the original function was utility function, if this was utility as a function of q instead of x, if I replace x with q, quantity now is an independent variable, the thing that we can change, right? This is from the perspective of a consumer, right? You don't change the price, you change the quantity, right? You react to the quantity, let's say. Then this first derivative would be called marginal utility. So yes, u prime, yes, you differentiate at utility once, but what you get as a result, his first derivative, we have a name for it, right? In economics, marginal utility. It's still a function of q, obviously, right? It's still a function of q, and it can be, yeah? So, but it's one order lower. So if you started with a quadratic, of course, every act of differentiation brings you by 1 degree down. So you go from 2 to 1, in this case. So now it's a line, right? Now it's a line that actually slopes down. It goes down. It starts at 400. So if you picture it, right? How would you picture this line? Exactly. Down with this particular rate. And you can figure out, right? To go from 400 down to 0, it has to basically experience a drop by 400, which means q must be 100. Minus 4 times 100, right? So by the time it gets to 100 in terms of q, it must be already on the ground. So now you have it, 100. You get it. Okay, so now what? Now you get a triangular shape, right? Now, you can find the area of a triangle. Easy, right? But we don't know why we would do that, right? What's the purpose of doing it, right? Let's think a little bit more about this. Let's talk about some other concepts there, the economic concepts. Okay, we got ourselves to the marginal utility now. What is the consumer surplus idea? Isn't that the difference? Yes, so there's another way of talking about utility. Let me do this. First stage, then we found the derivative. Okay, then we drew the picture of the derivative. This is, by the way, the derivative. This is the expression of minus 4q plus 400, right? Let's call it f, not x, f prime q, right? This is our f prime q, you know? We had our fq, that was our utility function, and now it's f prime q. Okay, actually we have a name for it, marginal utility, right? That becomes a marginal utility. That's also a demand curve, but in order to make it a demand curve, you will have to change the marginal utility to price. And there is a reason for that. Like, there's a logical reason why you can't do that, right? It kind of makes no sense. Like, why would I change marginal utility to price out of nowhere? What? Right? Why would I do that? Like, what? Who gives me that reason? Who gives me that right? Now, but it comes from the consumer surplus idea. Consumer surplus. What's the consumer surplus again? How would you get surplus in your happiness? Consumer surplus is what you gain from utilizing something. What does that mean? How do you gain something when you get more than you give?